Hey there, in this video we will learn about the preparation of alkanes. In the previous video we learned how we can prepare alkanes from catalytic hydrogenation of alkenes and alkynes, wherein what we used was hydrogen in the presence of catalyst. What catalyst? Yeah, nickel, platinum, palladium. Any of these metals can be used. So if you take alkene and add hydrogen to it in the presence of any of these metals, what you get is alkane. Similarly, if you're taking alkyne, then you need to add 2 moles of hydrogen in the presence of either nickel, platinum or palladium and you would get alkane. In this case, we have taken propyne and what we're getting is propane. Now my question to you is, can you prepare methane by catalytic hydrogenation? Well, you know that the smallest alkene which is possible is of 2 carbons and so is an alkyne. So yes, the answer is no, we can't prepare methane using catalytic hydrogenation. So let's try to know more methods of preparation of alkanes. Now let's make use of alkyl halides. So we can take alkyl halide and can treat it with zinc in the presence of dilute hydrochloric acid, or we can add sodium in the presence of dry ether. So let's see what happens in both the cases. Let's start with the first one when we take zinc in the presence of dilute hydrochloric acid. So you have to start with alkyl halide and you're carrying out reduction here. Why reduction? Because we know that we are just removing this electronegative element and replacing it with hydrogen. So you can think of it as addition of hydrogen is reduction, or removal of electronegative element is also called reduction, right? And the reducing agent that we can use here is zinc dilute hydrochloric acid. So if you take methyl chloride and add to it zinc in the presence of this acid, you get methane. There you go, you found out a way to prepare methane, haven't you? Well, what happens here is zinc reacts with hydrochloric acid to form nascent hydrogen. So this is what actually that causes reduction, this nascent hydrogen, which we represent like this. There is this hydrogen in the square brackets like this, okay? And this is quite reactive hydrogen. Now what happens? This can cause reduction and can help us replace this chlorine, and what we get is methane as a result. We also get zinc chloride as one of the byproducts along with hydrogen chloride, okay? Now if I take, let's say, propyl chloride in the presence of zinc and dilute hydrochloric acid, again what we get is a reduced product, that is the removal of chlorine with hydrogen giving us propane, right? Now my question is, what if we replace this chlorine with fluorine? In that case, if we add zinc and dilute hydrochloric acid, are we still going to get alkane? Well, turns out that this CF bond is very strong, and since it is very strong, cleaving this is very difficult, as the bond dissociation enthalpy of carbon fluorine bond is 485 kilojoule per mole approximately, which is quite high. So yes, if you're taking alkyl fluorides, you will not end up getting the alkanes that you desired. All right. Well, now let's look at the second method of preparation of alkane from sodium dry ether. Now this is a very interesting reaction. So here also you can just reduce alkyl halide and what you get is alkane, but the reducing agent that we are using now is sodium in the presence of dry ether. And this is the famous named reaction of chemistry called Wood's reaction. Okay, now what happens here is you can take 2 moles of alkyl halide. So you're taking actually the same alkyl halide like this. I'm writing it in this form, or you can also write it like this, 2Rx, means the same, okay? Reacts with 2 moles of sodium. So basically what happens? Think of it like this, that NaX gets eliminated out and 2R basically couples together, combines together. What you get is a step up reaction. You can see the alkane chain is going to become bigger. If this has 1 carbon, so if you have methyl chloride, you will end up getting ethane. Similarly, if you have 2 carbons out here, you will end up getting alkane of 4 carbons. If you have 3 carbons, you end up getting alkane of 6 carbons. You get it? Now, one interesting thing to observe here is this term dry. Why do we use dry ether? I mean, why not just ether? So the reason why we use dry ether is, number one, this sodium reacts vigorously with water. So even if there is a little drop of water, oh my God, that is going to be dangerous. We do not want a blast in our labs, right? So yes, we make use of dry ether. So dry ether helps in providing inert environment. So it's an inert solvent which prevents the interference with the reaction. All right. Now, you must be curious how all of this is happening. How is a step-up reaction like this where Rx is combining with sodium to give you RR? I mean, how is that even happening? Let's get into the mechanism. So here, what happens is sodium can easily give electron. We know that sodium loves to give electron and it has very low ionization enthalpy. So we can easily get sodium plus and one electron is removed out, which can be taken by X out here. So this halogen, which loves to accept electrons because it has high electron gain enthalpy, so it can accept electron to become X minus. As a result, what you get is R free radical. So think of it that this electron is leading to a homolysis situation here. As a result, what you get is X free radical and R free radical. The moment X free radical sees one electron nearby, it becomes X minus, and as a result, what you get is alkyl free radical. So you have decoded the intermediate of the reaction. It is this alkyl free radical which is the intermediate of the reaction. And what happens when two alkyl free radicals are going to see each other? Well, they desperately form a bond, and henceforth what you get is this step-up reaction where the two alkyl groups simply combine together. Now, this free radical mechanism is just one of the proposed mechanisms. There is another very popular mechanism which involves the electron transfer and the formation of carb anion. So unlike in the previous mechanism where you saw the formation of free radical, here we have the intermediate, that is carb anion, which is formed. Okay, so let's see how it happens. So what you see is this Rx molecule, alkyl halide molecule, right? And here is our sodium atom which donates one electron. Since it is donating one electron, this is also called SET step, single electron transfer. So ET is for electron transfer, and since it's just one electron which is being transferred, we are calling it single electron transfer. Okay, so this leads to kind of like a homolysis here that leads to the development of R free radical and X free radical, and sodium, since it has transferred one electron, we get X minus, which you can see is balanced with this Na plus. So you get sodium halide, and along with that you get alkyl free radical, right? Now, the next step involves another step in which there is single electron transfer. Look at this. So you can see this sodium again is doing a single electron transfer to this alkyl free radical, leading to the generation of R minus, which is balanced out by this Na plus that is formed after the sodium atom has donated one electron. Okay, so what now you have got is Na plus R minus. So now that you have this carb anion, the next step is the nucleophilic substitution reaction. So R minus, since it is electron rich, acts like a nucleophile, right? And this nucleophile attacks this alkyl halide. So you know that this carbon directly attached to halogen is delta positive, right? Because halogen is more electronegative, so delta minus. So this nucleophile attacks this electrophilic carbon from the back side. So if you have done already SN2 reaction, you know exactly what we are talking about. If you haven't, don't worry. When you do haloalkanes, you learn about this nucleophilic substitution bimolecular reaction in much more detail. But here, all that you can understand is this nucleophile attacks from the back side, leading to this carbon-carbon bond formation, and hence what happens is a coupling reaction, wherein the step 2 is a simple nucleophilic substitution. Along with that, what you get is X minus, so X here is a leaving group, and this is balanced out by the Na plus in the solution. So yes, what you get is this step up reaction. So the easiest way of writing this reaction is like this. Write one Rx like this, the other Rx like this, and sodium can be written in the center. So we need 2 sodium atoms so that we get 2 moles of sodium halide, and R and R combines together, giving you a step up alkane. So you can see that Wood's reaction will always end up giving you even number of carbons in the product. How can that be? For example, if my R is methyl, then what you end up getting is ethane. If my R is ethyl, then what you end up getting is butane. If my R is propyl, a 3 carbon, even if you're taking an odd carbon, what you end up getting is a 6 carbon product. That is hexane. So even in an even also gives you even. Odd plus odd is also going to give you even. That's the odd even chemistry out here. Okay. So my question to you is there any possibility whatsoever to get odd number of carbons in the product? Well, you might say, what if we take different alkyl groups? Say one is Rx and the other one is R-X. Okay. So when R is same as R dash, that means when both are same, the possibility of getting odd carbons in the product is not possible. So when R is same as R dash, only even products are possible, right? But what if R is not same as R dash? That's the situation when you can get odd number of carbons in the product, and not just that, you will end up getting multiple products. Let's take it with an example. Say if we take methyl chloride and ethyl chloride, then you can see that methyl chloride will lead to the generation of methyl free radical, and ethyl chloride will lead to the generation of the ethyl free radical. So when methyl free radical comes in contact with ethyl free radical, what you end up getting is propane. But don't you agree that a methyl free radical can come in contact with another methyl free radical? Because, hey, we have a lot of molecules in a reaction. It's not just 2 molecules reacting, right? We have a lot of molecules of methyl chloride. We have a lot of molecules of ethyl chloride. So there is a possibility that 2 methyl radicals come in contact with each other and form ethane, right? And this is also a possibility, that 2 ethyl free radical comes in contact with each other. That will lead to the generation of butane, you can see. And our byproduct is certainly sodium chloride. So you can see that what we are getting are mixture of products which are formed in this reaction. Okay. So as the mixture of products are formed, yield of the product is not going to be significant. Therefore, it's not preferable to use different alkyl halides. Now, here's a question waiting for you. The question says, which of the following alkyl bromides may be used for the synthesis of 2,3-dimethylbutane by Wood's reaction? Okay, so this is a very interesting question. You have to go retro, you have to go opposite. You know the product, you have to find out the reactant in this case. Do pause the video and find out the answer. All right, let's find out the answer to this question. For that, let's take a look at what is the final product that is getting formed. So we have 2,3-dimethylbutane. Okay, so this is the final product. Where do you think this would be coming from? Don't you think that if I would have had 2 such alkyl halides, then our product will be getting formed? So here X is bromine, right? So you can think of 2 moles of sodium going away with these 2 halogens to give you sodium halide. As a result, the free radical that is getting formed is this isopropyl free radical, and 2 such isopropyl free radicals are going to combine to give you this product. So what shall be your reactant? The reactant should be 2-bromopropane, which is in option B. So B becomes the answer. Let's also think of what other products are we going to get. So in option A, what we will get is, since it's N-propyl bromine, you will end up getting a straight chain of 6 carbons. So N-hexane. If you take option C, then what you will get? You can see that this is your skeletal structure. So bromine is here. So I am joining the other skeleton, the same skeleton other side also. So this is what you would get. So you can see that the number of carbons should exactly be double. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 8 carbons, and this is 1, 2, 3, 4, 5, and 6. So what you end up getting is 2,5 dimethyl hexane. Okay, and in option D, again 4 carbons are there. So what you should end up getting here, you have a bromine which is here. So 1, 2, 3, 4, and the coupling will happen from the second carbon because that's where the bromine is. So this is what you end up getting. So it is 3, 4, 5, and 6. So it is 3,4-dimethyl hexane. So yes, we have also revised the products that we shall get in all the options, but the right answer to this question is option B.